Welcome friends to my YouTube channel. On my last lecture, I have discussed about the Kelvin scale of temperature. Okay, and I also discussed few similarities between perfect gas scale and Kelvin scale temperature. Now, let us try to find out another similarity between these two in a more general way. So, in case of a perfect gas scale, okay, we have q1 upon q2, this is equals to t1 upon t2, where the reversible Carnot engine absorbs q1 heat from source at temperature t1 and rejects q2 heat to sink at temperature t2. Okay, and that for Kelvin scale temperature we get q1 upon q2, this equals to tau 1 upon tau 2, and from that we see that T1 upon T2, this is equals to tau 1 by tau 2. So this is one similarity that we found, that the ratio of any two temperatures in both the gas scales are equal. So this is one. And another similarity that we found, that for, if you look back the equation of of reversible Carnot engine for a perfect gas scale, and if you make Q2 equal to 0, then T2 becomes 0. Okay, and in this equation if you take q2 equal to 0, then tau 2 also 0, and so 0 of both gas scales, 0 of both gas scales coincides. Okay, and from which we define the absolute 0 of Kelvin scale temperature, that is the temperature at which the reversible Carnot engine does not reject any heat to sink is called absolute 0 of Kelvin scale temperature. Okay, 0 of Kelvin scale temperature. Okay, so this is another similarity. Now let us try to find out another similarity, okay, which is nothing but the size of Kelvin degree. Okay, now let us try to find out the size of each Kelvin degree. Okay, we are talking about the Kelvin scale temperature, so let us check what is the size of each Kelvin degree. Okay, now here we consider successive reversible engines, that is, this is first engine, this is second engine, say this is third engine. We consider successive reversible engines. Let the first engine absorbs q1 heat at temperature t1 and rejects q2 heat at temperature t2. Okay, and the second engine absorbs that amount of heat which was rejected by the previous one, so it will also absorb q2 heat and reject, say, q3 heat at temperature t3. The third engine will absorb this amount of heat and, say, reject q4 amount of heat at temperature t4. Okay, so we consider several engines. Okay, several reversible engines. Okay, we consider. Now the first engine absorbs q1 heat from source at temperature t1 and rejects q2 heat to sink at temperature t2. So for first engine, what we can write? So for first engine we can easily write q1 upon q2, this equals to t1 upon t2. So from which we can write q1 upon t1, this equals to q2 upon t2. Okay, this gives the name equation 1, say. Now the second engine absorbs q2 amount of heat at temperature t2 and rejects q3 amount of heat at temperature t3. So what we write for the second engine? For the second engine we can write q2 upon q3, that is equal to t2 upon t3. So from which we can easily write q2 by t2, q3 by t3. Okay, And in this way, for the third engine, we can easily write Q3 upon T3, this equals to Q4 upon T4. Okay, so this we write. So in general, what we can write? We can write Q1 upon T1, this equals to Q2 upon T2, this equals to Q3 upon T3, this equals to Q4 upon T4, dot 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 dot. So this is the equation that we can write. Okay, now we all know from mathematics that if we can write this line, that is the equation 3. Okay, if we can write equation 3, okay, if we can write equation 3, that is this, then this also equals to what? This also equals to this also, that is, I write here Q1 upon T1, this equals to Q2 upon T2, this equals to Q2 3 upon T3, Q4 upon T4. Okay, dot dot dot. So this must be equal to what? Q1 minus Q2 by T1 minus T2 equal to Q2 minus Q3 by T2 minus T3 equal to Q3 minus Q4 by T3 minus T4. A by B equal to C by D equals to A minus B by C minus D. That formula here we have used there. Okay. Now what is our assumption? Now our assumption is that the engines are coupled in such a way that work done by each engine in every cycle is same. Okay, this is the assumption. Okay, all engines are coupled in such a way that work done per cycle for each engine are equal. So that means what? That means W, this equals to Q1 minus Q2 equals to Q2 minus Q3 equal to Q3 minus Q4. This is okay. So that assumption we have to make. So if we substitute these values in this equation, then what we get? So from above equation we can write T1 minus T2, this equals to T2 minus T3, this equals to T3 minus T4, dot 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 dot. So we have arrived at that point. So it is clear that if the first engine absorbs heat from say you can take 100 reversible engines. Okay, suppose you take 100 reversible engines, then what happened? For 100 reversible engines, we all know that the first engine absorbs heat from steam point and the last engine rejects heat to ice point. Okay, that is the first engine absorbs heat at 100 degrees Celsius and the last engine rejects heat at 0 degrees Celsius. Okay, and in between these engines, a particular engine absorbs that amount of heat which was rejected by the previous one. Okay, which was rejected by the previous one. Okay, so if we select 100 engines, if we consider 100 engine, so the first engine absorbs heat from steam point and last engine rejects heat to ice point, and in between these 2 points a particular engine absorbs that amount of heat which was rejected by the previous one. So there are 100 equal intervals and each interval is called 1 Kelvin degree. ঠিক আছে, each interval is called Kelvin degree. Okay, this is common. So if we consider 100 engines, then there are the first engine absorbs heat from steam point and the last one rejects it to ice point. And if a particular engine absorbs that amount of heat which was rejected by the previous one, then we can define 100 equal intervals of temperature, which is called Kelvin degree. ঠিক আছে, equal interval say of temperature, and this is called Kelvin degree. Okay, so each have 1 Kelvin degree. Okay, so this is the comparative study of similarity between perfect gas scale and absolute gas scale. Okay, so with this I have completed the heat engine. Okay, now today I shall mention refrigerator. Okay, I will give brief introduction that what is refrigerator. Okay, what is refrigerator? Just I am going to talk about what is refrigerator. Okay, now what is a refrigerator? If all the operations of a reversible Carnot engine are performed in the opposite direction so that it absorbs heat from sink and rejects heat to source, then it is termed as refrigerator. That means in previous case the engine was absorbs heat from source. That means it absorbs heat from a high temperature body and gives heat to low temperature body. But this is reverse. It absorbs heat from sink. Okay, it absorbs heat from sink and give heat to source. That means it can cool a cooler system and further it can cool a cooler system. Okay, that means the sink is already at lower temperature, so if heat is extracted from it, then its temperature falls down, and source is at already high temperature. If heat is added to it, then its temperature will also raises. Okay, so it is extracting heat from a lower temperature body to high temperature body, but this is not possible generally. When it is possible, if we supply some external energy from outside, then heat will flow from cold body to hot body. Unless and until it will not flow from cold to hot body. Okay, so we have to supply some mechanical energy from outside. Okay, so if Q2 is the heat energy absorbed from sink and Q1 is the heat rejected to source, then it cannot be possible unless and until we supply few external energy or work from outside. Okay, that means Q2 heat is extracted from sink and we apply external energy, then it moves to, then it goes to source. So what will be my W? W is Q1 minus Q2. Okay, okay, so here W is the energy supplied from outside. Energy supplied, just dear guys, just leave the sound which was coming from outside. Energy supplied from outside. Okay, so when all the operations of a reversible Carnot engine are performed in opposite direction, are performed in opposite direction, it is called refrigerator. Okay, it is called refrigerator. So we see a refrigerator absorbs heat from a body of sink and gives it to source. So it is not possible unless and until we supply some external energy from outside. Okay, so if W is the mechanical energy supplied from outside, then W equal to Q1 minus Q2. So here W is the energy supplied from outside. Okay, now since refrigerator is also a machine, it will have a efficiency, and we call it the coefficient of performance. Okay, since the refrigerator is also a machine, there is a efficiency of the machine, and we call it coefficient of performance, which is denoted by beta. The coefficient of performance of a refrigerator is defined as the ratio of heat absorbed from sink to the external work done on the machine. This is the definition: heat absorbed from the sink to the work done on the machine. So if we write it, W equal to Q1 minus Q2. Okay, so if we now for a reversible Carnot engine, we all know Q2 by Q1, this equals to T2 by T1. Okay, so if we substitute divide it by Q1, then what we get? 1 minus Q2 by Q1. So this is simply T2 by T1, and this is 1 minus T2 by T1. So this is simply T2 by T1 minus T2. So this is also an expression of coefficient of performance in terms of temperature. Okay, so this is called coefficient of performance. Okay, so thus we see there are two expressions. One is Q2 upon Q1 minus Q2, and another is T2 by T1 minus T2. Okay, so this is the coefficient of performance of a refrigerator. Okay, now in our next class we will discuss about few other topics related to refrigerator and few conceptual questions. So dear guys, if you don't subscribe my channel, then kindly subscribe it to get latest updated videos on physics. Thank you.